If you recall, Gibbs free energy is a great way to describe the spontaneity and temperature dependence of a reaction. So in this video, what we're going to do is take a look at how Gibbs free energy is related to the equilibrium constant or an equilibrium system in general. So remember, a spontaneous reaction is when delta G is negative, non-spontaneous is when delta G is positive, and it is a really good indication of whether the forward or the reverse reaction is favored. So if delta G is negative, it means the forward reaction is favored. If it's positive, it means the reverse reaction is favored. Okay, so just something to kind of keep in mind. And we can calculate delta G, if you remember, from delta H minus T delta S. So what is then the relationship between delta G and the equilibrium constant, or K? When K equals 1, it means that we're at equilibrium and neither the reactants nor the products are going to be favored. And so what you would see with delta G is that the delta G would also be 0. And that's because it's not going to favor either the forward or the reverse reaction. If the equilibrium constant is bigger than 1, it means that the products are favored or the forward reaction is favored. And so that's going to give you a delta G that is negative, or a spontaneous delta G. If the K is less than 1, it means reactants are favored or the reverse reaction is favored. And so delta G would give you a positive value or a non-spontaneous type of value. Now, I think one thing to kind of keep in mind and note is that the position of equilibrium is going to correspond to a maximum value of entropy, so a maximum amount of disorder or randomness in the system, as well as a minimum in the value of the Gibbs free energy. So when a system hits equilibrium, you're going to have maximum entropy and minimum Gibbs free energy. Now we can relate the delta G value with temperature and the equilibrium constant with this equation here, where we got delta G is equal to negative RT ln of Kc, where delta G is the Gibbs free energy in kilojoules per mole. R is the gas constant, and that's in joules per Kelvin per mole. So take a look here. We got kilojoules and we got joules. So we're going to have to do a change in units when we're doing any calculation with this particular equation. Temperature is in Kelvin. And then K is the equilibrium law constant, which has no units. So let's take a look at an example and see how this all kind of fits together and how we can use these equations. So we're going to calculate the equilibrium constant at 300 Kelvin for this particular reaction here. So we want to know what Kc is for this reaction. We're given the delta H and the delta S and temperature. So the first thing we want to do is calculate the delta G, because we need that value. So we're going to do delta H minus T delta S, and we're going to plug in our values. So delta H is in kilojoules per mole, negative 82.42. And then we're going to subtract the temperature, already in Kelvin for us, but we'd have to do that conversion if we didn't have it. And then our delta S is in joules. So negative 270.5, and we have to divide that value by 1,000 to get that in kilojoules as well. So if we do this calculation, I get negative 1.27 kilojoules per mole. Okay. From here, if we want to get Kc, we got to use delta G is equal to negative RT ln K. Or if we rearrange this, the ln of Kc is equal to delta G, or negative delta G over RT. So plugging in our values, we got negative 1.27 for our delta G, kilojoules, so keep that in mind. You can multiply this one by 1,000 to put it into joules, or you could divide the R by 1,000 to get it into kilojoules. Doesn't really matter which way you go about it. But let's plug in our other values here. And then let's put this stuff up here. Ln of Kc, I'm getting, let's see, 0.5094, so on. And then if we take e to both sides, we'll get our Kc value of 1.66. So that gives us a Kc now for this particular reaction. And then we could do what other kind of equilibrium calculations with this particular chemical system. So that's a nice way to see how delta G and Kc relate to each other. That's it for this video. We'll see you in the next one.